So what I will present is a joint work with my supervisor, Massimiliano Gubinelli, who is also from Bonn, and the topic will be noiseless regularization by noise. So the title is a bit provocative. Of course, there will be noise, but I hope by the end of the talk to make you understand what I mean by noiseless. So, okay, the goal is to study the following. Easiest to formulate in regularization by noise phenomena, but also one of the most interesting. So I want to understand under which conditions on the additive perturbation W. Now this ODE, written in integral form, is well posed, even if the original without W wasn't. So, okay, this is a very old problem. This type of phenomena were first observed by Zonkin and Veretennikov when W is sampled as a Brownian motion. And indeed, most of the literature focuses on a probabilistic approach to the problem, which, however, has several drawbacks. So the first point is that indeed proofs heavily rely on stochastic calculus, because I mean, if W is Brownian motion, you want to use this information. But this also means that those methodologies do not extend to non-semi-martingale perturbations. And unless your model is very specific, there is in principle no reason why you should only consider semi-martingale perturbations. And again, since there is stochastic calculus, stochastic integrals will appear, which in general only define as random variables on the binary space. And so the notion of uniqueness we will obtain is pathwise uniqueness, which means any two solutions will actually be random variables, and you can compare them up to probability zero measure sets, where the set actually depends on the pair of solutions you're comparing. And similarly, uniqueness only holds in the setting of adaptive solutions, which, for instance, also gives several problems if you want to do time reversal. So, I mean, like adaptiveness, pathwise uniqueness are natural requirements in the probabilistic setting, but completely extraneous from the original problem when there was no perturbation. So what we want to pursue here is an alternative approach. So effectively, it amounts to exactly separate the analytic and probabilistic part of the theory. So we want to first identify analytical properties of the path, which ensure well-posedness, and then to find examples, like stochastic processes, to satisfy these properties almost surely. And early works in these directions are the one by Davy and Catellier and Gubinelli. The literature on regularization by noise is really vast. I mean, there are lots of other contributions, like there is Alexander work, which revisits David's result, or there is, for instance, the Beck, Flandoli, Gubinelli, Maurelli paper, which also gives another very interesting perspective. But for the approach that I will present here, these are really the two precursors. So, okay, with Massimiliano, we actually did two works on this because there are two different problems to consider. So the first one is to say, okay, I have a given model, I have a given fixed P, I want to find conditions on the perturbation to regularize this or the. So these will be conditions tailored on B. And the good notions to carry out these programs are nonlinear Young integrals and average fields, and this is what I will most present today. But the second problem instead is to say, okay, I want to find conditions on the perturbation to regularize a whole class of possible ODEs, so for a whole class of possible Bs. And here you need some additional concepts like occupation measures and local time. And this is what we studied in another paper. And while we were working on this, there was also a very nice paper by Nicolas and Fabian that came out on arXiv. So you can already see, like, answering the second problem gives you a lot more structure than the first one, because at that point you can truly consider random fields P. You can allow them to depend on W itself, or you can, for instance, allow the presence of an external control. So study control problems, you have a lot more, but it really comes at a higher price. I mean, the reason why I'm making this distinction is because there are truly cases, for instance, depending on whether the drift may depend on time, or depending on whether W has a given regularity and the dimension you live in, which is possible to answer positively to the first one and negatively to the second one. So before going further, let me quickly recap some of the theory. So for the unperturbed problem, W equal to 0, the first very well-known result is the Cauchy-Lipschitz one. So if B is local Lipschitz, then we have local well-posedness, which can then be extended to global well-posedness under, for instance, linear growth. And we not only have well-posedness, we actually have a flow, which is also fairly regular, and this also allows to solve the associated transport equation. So the Lipschitz condition can be relaxed, but it's fairly sharp. I mean, as soon as you try to consider an older continuous drift, there are a plethora of counterexamples of infinitely many solutions starting from the same initial data. At the same time, there is Peanut theorem, which guarantees you that if B is at least continuous, then we have existence of solutions. So there is effectively a regularity gap between what is needed for existence and what is needed for uniqueness. And this is already a regime in which it is interesting to explore regularization by noise phenomena. So if you're into transport theory, you know that actually this is not the end of the story. there is a whole part of the modern part of the theory, which was developed by Di Perna, Leon, Ambrosio, and then Kripa, Delelis, and their collaborators, which actually allows to consider B in some Sobolev space. But here I really want to define and study a Cauchy problem, so to deal with a given initial detect zero, and this type of theory doesn't allow me to do that, so I will not consider it here. And also, let me say, all the results I presented here immediately extend to the case of an additive perturbation W, because really all the proofs can be immediately readapted in this case. So Catellier and Gubinelli's idea is the following. Okay, now consider the perturbed ODE. Say for now that B is a continuous drift. So everything is well defined, all the manipulations I will do are rigorous. So the first observation is the following. If we make the most trivial change of variables, so we introduce theta as the difference between the solution X and the perturbation W, this will now solve a more classical ODE in integral form, but now W will appear inside the drift. So this actually immediately tells you that any solution must be of the form W plus a more regular term. So really the key point is if you want to develop a solution theory, like to set a fixed point, you shouldn't do it in the space of all possible continuous paths X. You should do it in the space of paths which have this kind of structure. And the second observation is that, okay, let me now define this object, TWB, which I will call an average field. Basically, it amounts as taking integrals of the drift B along the path W up to possibly shifting it by Y. Then the observation is the following. Okay, theta satisfies an integral equation. I can now split the interval over 0t into intervals over subintervals. And on each of these subintervals, I can actually freeze theta to take the time instant equal to the initial time and still allow WS to vary. So of course, this will create an error term, but the point is that everything is continuous, actually uniformly continuous. So as the mesh of the intervals go to 0, this type of error will become infinitesimal. So in the limits, this inequality, this identity is still true. And so now with the previous notation, I can actually write it in this way. So the point is that there is some kind of generalized Riemann-Stieltjes sum appearing because I'm taking a time increment of the average field, TWB, evaluated along the curve theta at the initial time of the increment Ti. And indeed, what they realized, is that now this object can not only be interpreted as a Lebesgue integral, it also has an alternative interpretation as a nonlinear Young integral. So let me introduce Young integration, nonlinear Young integration. So given a drift A, which I will allow to depend both on space and time, I will use this notation. It's just an incremental notation when I fix X. So we'll say that A is in C alpha C beta, where alpha and beta are parameters between 0 and 1. If the combined space-time increment can be controlled by the time increment to some exponent alpha times the space increment to some exponent beta. Okay, more precisely, I will say that it's in C alpha C beta if this condition holds. And I also have similar controls for the time increments at fixed X and for the space increments X fixed T. Okay, so these are all gonna be global bounds. I mean, one can relax them to local bounds, but it's a bit more technical. I will not do it here for simplicity. So, okay, these optimal constants will actually define a semi-norm and a norm respectively. And one can also say that A is in C alpha Cn plus beta if all the spatial derivatives up to order n will have this type of property. So, okay, one of the main results by Catellier and Gubinelli is that, okay, if now A has this kind of C alpha C beta regularity, and I consider a curve that theta, which is gamma order continuous, okay, if I impose that alpha plus beta gamma is strictly greater than 1, then now this Riemann-Stieltjes sum, the limit as an integral, can be rigorously defined. So in particular, okay, here I did this only for capital T, but actually this quantity can be defined for any small t between 0 and capital T. And so actually this will define a time-dependent function, which can be shown to be alpha order continuous. So it will inherit the time regularity of the original A. Moreover, one can show that the map that A and theta associates this kind of interval along the curve theta of the drift A is going to be continuous in the respective topologies. So by this, I mean that A has the topology induced by the alpha beta norm, and instead theta and the image have older continuous norms. And the idea of proof, if you're familiar with generalized Riemann-Stieltjes sums, is as always to apply the Sewin lemma. So effectively, one can define this gamma and only needs to provide a good control on the third order generalized increment. And indeed, one can apply the hypothesis on A and theta to actually check this. I mean, one will obtain a control by T minus S to the power alpha plus beta gamma, which by hypothesis is strictly greater than 1. So one can apply the Sewin lemma to conclude. So, okay, having defined this concept of nonlinear Young integrals, we can also study nonlinear Young differential equations. So the idea now is that the drift A is given, initial data θ0 as well, and we want to find θ satisfying this fixed point relation. Indeed, a solution theory can be developed and goes as follows. So if A is going to be C alpha C1, then existence is granted for any initial data. If we require 1 degree of regularity more, so C alpha C2, now we will actually have uniqueness of solutions, and moreover, one has a flow, which is going to be a flow of a Lagrangian flow of diffeomorphisms to this equation. And moreover, one has stability estimates. So effectively, if now we consider 2 different drifts AI, which are in C alpha C2, 2 different initial data, and we consider the solutions associated to this data, they will depend in the alpha older norm, effectively in a Lipschitz way on the data of the problem. So the proofs are a bit sparse in the literature. Most of them are already present in the Catellier and Gubinelli paper. Hu and Le independently redeveloped the nonlinear Young integrals, and they were the first ones to show that actually the flow is not just a Lipschitz flow, it's a flow of diffeomorphisms, and it's also Lagrangian. And we also revisited and further expanded the theorem in our work, the theory in our work. So, okay, back to the original problem, because the reason why I introduced all this abstract nonlinear Young differential theory is because the key observation was that if X is a solution to the perturbed ODE, it's going to be of the form W plus theta, where now theta solves a Young differential equation with drift given by the average field, TWB. And so we can indeed apply all the previous theory and deduce that if the average field is on a regularity C alpha C2, then uniqueness holds. What is really interesting at this point is that really all the regularity requirements now are only on the average field TWB. The regularity conditions of B do not appear anymore in this kind of statement. And in particular, moreover, the average fields can also be defined when B is just merely distributional. So this is just a technical lemma, but basically what it says is that if we consider B distributional, like here in some spatial Bezold space of regularity, we can still define the average field, TWB, which is going to be itself a distribution. So it will not have point-wise meaning, but it will have the same type of spatial regularity than B. But okay, it now makes sense to talk about TWB, and moreover, it will have all the nice properties we wanted to have. So like this property of averaging will commute with spatial convolutions, so in particular with modifiers, and also, for instance, with spatial derivatives in the sense of distributions. And so in particular, if we assume that now the average field has higher regularity, like C alpha C2, we can also successfully approximate it by considering the averaging of modified fields in the same regime regularity, okay, up to giving up epsilon because we are in older spaces. Okay, so now we can actually extend the previous theory to distributional fields, because now really the point is that this equation will just become convenient notation. I mean, B is distributional, so we cannot evaluate it in X. This does not make sense as a Lebesgue integral anymore, but we can still say that X is formally a solution to this equation if it has the following form. It's going to be W plus theta, where now theta satisfies the following Young differential equation, which is well defined. And so there is a nice analogy with rough theory in the following sense, that if you really want to give a good solution theory for this perturbed type of ODEs, you shouldn't just consider the data of the problem to the drift P and the perturbation W, but you should really take into account the information on the regularity of the average field TWB. So once you pass from the data of the problem from in this couple to this triple, if TWB is sufficiently regular, now the solutions will depend continuously on the data of the problem. And moreover, actually, these generalized solutions can be reconstructed by smooth approximations. So in particular, if TWB is alpha C2, then okay, we can first modify spatially the drift. Now B epsilon is going to be spatially smooth. So the classical ODE for B epsilon will make sense. It will be well posed. So given X epsilon, the solution to the classical modified ODE, one can actually show that as epsilon goes to 0, X epsilon will converge to X, which is the unique solution in the sense of this definition. So it's really a nice solution theory. I mean, you have a continuous dependence on the data of the problem, and you can always modify with more, approximate with more classical solutions. And also with this kind of theory, one can approach the problem of perturbed transport equations. So, okay, again, this is the simplest type of linear transport equation with this kind of perturbation. And this here is just convenient notation. I never impose W to be differentiable. Indeed, in the interesting cases, it will not be. So what I mean by this is that, okay, assume everything for a second to be smooth. So we can do the most trivial change of variables. So we can define U to be the solution W shifted by, sorry, the solution B shifted by W, and similarly B tilde for B. And now U and B tilde will satisfy a transport equation in which W dot does not appear anymore. And this change of variables is defined meaningfully when W is just continuous. So this is the exact equivalent at the Eulerian level of the previous change of variables of passing from X to theta at the Lagrangian level. So I will actually say, okay, V is a solution of this equation if and only if U defined in this way is a solution to this one. And if you're familiar with rough path theory, you know that this reasoning, I assume everything smooth first and then I go by approximation, is not entirely naive. Effectively, this means that if W is a rough path, and so this actually has a meaningful interpretation, in order to have consistency, you really need W to be a geometric rough path. And okay, if this distributional, now this is still convenient notation, is not meaningful. We need to relax it further and take the integral in time. So I will say that U is a solution now. If its gradient is well defined, it is sufficiently regular. And now this type of integral relation holds, where now this is a Young integral, because TWB, remember, has some C alpha regularity. And what one can show is that, again, if TWB is C alpha C2, then for any sufficiently smooth initial data, one can indeed show that there exists a unique solution to this type of equation, which is given, not surprisingly, by the initial data U0 evaluated in the back to labels map. This is the inverse of the solution map to the associated ODE. And moreover, since the flow is Lagrangian, the solution map successfully extends to any U0 satisfying some of the condition. And moreover, one can actually also give similar results for the continuity equation. So, okay, the continuity equation will be defined for measure value solutions. So one needs to give a weaker definition, a variational type of definition for the solutions, but it still can be done. So all of this was the first part of the program. So to find analytical conditions on W on the form of the regularity for TWB, under which we have this regularity. So now the next step instead is to find examples of W having this regularization property. So indeed, this can be done. So one result is that if now W is sampled as a fractional Brownian motion of parameter H, and for instance, we consider B to be an infinity in time of C alpha in space, here alpha can be negative, so it's going to be a Bezold space. Here, by this, I just mean that it's going to be compactly supported with the support being uniform in time. It's a bit of a technical condition. So anyway, what one can show is that now TWB will belong to C1 C alpha plus 1 over 2H. So there is indeed an improvement in spatial regularity of order 1 over 2H. And so in particular, at this point, you can check by hand for suitable choices of alpha and H if you reach the C1 C2 condition. And indeed, in particular, you can observe that H is allowed to be between 0 and 1. So in particular, taking H sufficiently small, this condition, this condition will be satisfied for any alpha. I mean, you fix alpha, you take H sufficiently small. Similar results can be given for more general processes. The common key property is that these must be Gaussian processes satisfying a local non-deterministic condition. But also one can start asking different type of questions once you have already solved the first problem of the program. Because one cannot ask, for instance, okay, what happens if I consider generic continuous perturbations? And indeed, one result we prove is that for almost every path in C delta, so delta order continuous, indeed, the average field TWB is going to be of regularity C1 C alpha plus 1 over 2 delta. So this almost every or generic condition here must be interpreted in the sense of prevalence. So prevalence is a theory that was first developed by Christensen and then later rediscovered by Hanshauer and York. And basically it allows you to define full Lebesgue measure sets in infinite dimension. I mean, okay, the Lebesgue measure will not be well defined in infinite dimensions, but you can still at least consistently define this notion. So indeed, by this property, I really mean the set of W belonging to C delta, which satisfy this, is a prevalence set. And this is really what I mean by noiseless here. Because really the point is that this kind of statement now has no condition whatsoever on an underlying probability space. It's really an analytic statement of generic perturbations. Okay, and I think my time is up. So, okay, we'll leave this slide for all the interested readers on related works and future projects, but I will stop